we are starting a new chapter today, and we're going to look at the introduction to probability. So I would expect that most people have heard of probability in some place or other. It does appear. I mean, it appears in gambling, of course. You'd expect it to appear there. But, you know, it appears in weather. Don't you get things like there's a 30% chance it's going to rain tomorrow, you know?
Yeah.
Yeah, so probability is an idea, a concept that is widely known, that's used in all sorts of places. And so let's start right at the beginning. We talk about, this is probability of an event A happening. We normally would write that for short as P of A. So that says probability. I've missed some A's and B's in there, but you know what it's meant to say. Probability of event A, written as that, or you sometimes see in some textbooks it written like that. And what do we mean when we say the probability of event A? Well, what we're really saying is the proportion of times you expect event A to happen. So let's give you a story. Suppose we are rolling a dice, nothing special, right? Just a normal dice. If I said to you, what's the probability that you get a 3? We could write it short by just saying that, right? That means the probability that you roll a dice and you get a 3. But we don't need all the English, that'll cover it. It's made up of 2 numbers. The top number is the number of ways to get event A. In this particular simple question, it's how many ways can you get a number 3 on a dice? Would you agree there's only 1 3 in a normal dice? So that is going to be 1. And on the bottom, it's a total number of things that could happen. Well, there are 6 things that could happen. And so the probability that you roll a dice and you get the number 3 is 186, right? It's a 6th. Now we could write that down as 0.167 roughly if you do a decimal, or we could write it down as 16.7%, because probabilities are written down as fractions, proportions, and percentages. They are the same thing. Would you agree that 16.7 is roughly a 6th, right? They're the same thing, just different ways. So when you're answering questions, just be on the lookout for what they want. If they say, give me the probability as a fraction, do that. If they say, give me the probability as a percentage, do that. I think those 2 are the easy ones. But when they say, give me the probability as a proportion, they may or may not say, and to 2 decimal places or whatever. They're talking about this guy. So what about the probability that you roll a dice and it's an even number? Right, there's a 6 on the bottom. Of all the numbers on the dice, how many of them are even numbers? Agreed, 3. And we always simplify fractions. So don't leave it as 3/6, call it a half, right? Don't leave it as 4/10, call it 2/5, right? It's a pretty common rule that you don't or shouldn't really need to be told if you just take it for granted. So are we comfortable about what we mean when we say the probability of an event, right? It's a proportion of times you expect that event to happen, right? If you did it lots of times, what fraction at the time would be another way of saying that. So if you imagine any event A, anything at all probabilities are in the range 0 to 1 if you're talking about proportions, or 0 to half, it's a fraction. Nah. Change the pen. At this point here, the probability is 0. Things that have a probability of 0 are never going to happen. Would you agree? If somebody says the probability of that is 0, that means it ain't going to happen. What would that be like? The probability you talk to a politician and he always tells you the truth. That would be a 0 event, right? Well, you know I don't like politicians, so that's not a surprise to you. What does a probability of 1 mean in English?
It's going to happen.
It's going to happen. It will happen. And if we do percentages, won't that just be, if the probability is given as a percentage, doesn't that mean that the answer is always going to be somewhere between 0 and 100%, right? That's the same as 0 and 1. Now, let's pick somebody right in the middle, up there. 0.5 is a decimal. If you prefer, I'll call it a half, right? Now, when you get probabilities that fall in the middle, we have some English terms that you might have heard that we use when these situations pop up. If you heard phrases like there's a 50-50 chance it's going to rain tomorrow, that would be a probability of a half event, right? Or is just as likely to happen as not. That would be another way of phrasing this situation, right? We have in the English language some phrases that basically are telling us it's a 0.5 or 50% chance of happening. So that's right in the middle. Now, as you travel towards 1, aren't these things going to be more likely to happen? So if you have a probability, if you have a probability of 0.9, would you agree that that is probably going to be something that's very likely to happen a lot more times than not happen? That makes sense, right?
We lost picture.
You did? Am I here?
Yep. Oh, we lost what you were showing us.
We here?
There we go.
Okay, thank you. I'm weird issues today. Right. And if you go this direction, isn't this things that are less likely? So if something has a probability of 0.0001, isn't that one of those things that probably never happens, except like once in a blue moon, right? Like, oh, it happened. Like Barbara giving birth to triplets. Not happened yet, right? But I bet you if you asked enough people in your job, wouldn't you probably find eventually one person who said, yeah, it happened to me once. I was there when it was triplets, right? But it's a very unlikely event. And we cannot understand that the bigger the number is, isn't it, the more likely to happen. But probability is our way of putting a number on how likely. It makes sense, doesn't it? That you would want a number to try and qualify that rather than say, it's very likely to happen or it's very unlikely. Isn't that far too vague? You can't really compare things when you use terms. But if I say 0.9 and 0.7, isn't the 0.9 thing going to happen a little bit more often than the 0.7 thing, whatever those things are? And that is a useful thing to be able to calculate. So we're now going to move on to a thing called the complement of event A. And it is written as A with a little c, although that's what they use in this book. But in case you look at other things, I've seen it called A with a little dash on it. I've even seen A with a little T on it. But A with a little c is what WebAssign uses, so that's what I'm going to use. So the complement of event A. So let's give you an example of 2 events. Event A is you roll a dice and you get an even number. Right, so I roll a dice and I get an even number. What would the complement of A be? So the complement of A is the opposite of that, right?
An odd number.
An odd number. So complement of A is the opposite of event A. Haven't really done enough of these to show you. Oh, here we go. Hopefully you're aware of cards. Suppose A was the event that I picked a club. What would the complement of A be?
Picking any suit besides club.
Correct. So in English, you might just say not club. Actually, not's a good idea. Complement is like not A, right? That's another way of looking at it. In this case, then it would be you've got a heart or a spade or a diamond. Now, these two probabilities, the A and the complement of A, are actually connected by a very simple formula. The probability that you get event A plus the probability that you get the complement of A is always equal to 1. Does that make sense? Why that would be true? The probability that something happens plus the probability that it doesn't happen is always going to add up to 1. So suppose I don't even tell you what the event is, but I tell you that the probability of event A is 0.8. Can't we now find the complement of A? Even although we don't know what the event is, we can tell its probability. What would the complement of A be in that question here? Agreed.
0.2.
0.2. Don't you just take it away from 1 and what's left is the other guy? It's a bit like a seesaw, isn't it? As one goes up, the other compensates and goes down. Yeah. They both add up to 1 at every instant that is as an event. Are we comfortable with the concept of what the complement of event A is? Feel we're good, okay. So let's whoops, wrong way. Let's now look at, it's called the sample space. When you do probabilities, the bottom number is how many ways the thing could happen, right? And the top number is how many ways, sorry, I'll get that back to front now. The bottom number is the total number of things that could happen, right? And the top number is how many ways A can happen, right? That's essentially it. So if you want to know a probability, don't you need to know all the things that could happen as well as the things you're interested in? So that's what a sample space is. Sample space is a list of all possible events. So suppose we are doing coins, a single coin, right? One coin. The sample space would just be 2 things, right? It's a head, but it's a tail. So if you were doing questions to do with coins, wouldn't the bottom number be 2 and the top number depends on what the story is? Now, suppose we do a dice. Wouldn't the sample space be those guys? And when you're doing probabilities with dice, because there are 6 things here, won't the bottom number be 6 and the top number is whatever the question happens to be? So if I said to you, what's the probability that it's a 2, you'd say 1/86. If I said it was even, you do 3/6 and so on. But won't the bottom stay put, right? It's 6 in that space. So far, so good. Now, I got a little list of guys here, so I don't have to rewrite them. And you might already know them. There are lots of questions in probability to deal with cards. Oh, Isabel, what's your question?
So what would be the numerator for those, because we have the denominator is the number of items in the list, the number of possibilities. For like the coin, it's 2, for the dice, it's 6. But what's the number on top? Is that just 1?
Well, it depends on the story. So if you were doing a dice question, if I said to you, what's the probability that you get the number 3? You would say 1 on the top. There's only 1 3 out of 6.
Okay,
if I
so that was
said
just
what's
how to
it-
get the denominator then.
So yeah,
Okay.
the numerator depends on the story, but the denominator is always going to be 6 when it's a single dice.
Okay.
Now, let's look at cards. There are 52 things that can happen in a normal deck of cards, right? That's cards that don't have jokers or anything weird going on, right? And this here is a kind of quick summary because not everyone's familiar with cards. They're called clubs, spades, diamonds, and hearts. They're the 4 suits. And the clubs and spades are black cards, and the diamonds and hearts are red cards. Isabel, question.
I just forgot to put my hand down, my bad.
Okay, right. So 4 suits, 2 of them are black, 2 of them are red. Each suit has 13 cards, starting with the ace, which is typically worth 1 in sometimes 11, but it's the first card, ace, all the way to 10. And then the last 3 cards are called Jack, Queen, and King. And Jack, Queen, and King are called face cards. If you look at them on a deck of cards, there's a person's face, right? A queen's face or a king's face or the jack's face. So the sample space there, I'm not writing them all down, but can you see that would be 52? So let's use some probabilities involving decks of cards. For instance, if I said to you, what's the probability that you get a king when you pick 1 card from a deck? The bottom is 52, right? Because we know that. How many of those 52 are kings?
4.
4.
Agreed. And then you simplify it down. Now, suppose I went and said to you the probability that it's a face card. Do you notice that the bottom number is still 52, but don't we need to count all the face cards? And there's 3 of these, 3 more, 3 more, and finally 3 more. Are you happy about the 12th? And 4, that's 13, 3 13s. Okay. And suppose I said to you, what's the probability that it's a red face card? Still 52 in the bottom, but how many of the face cards are considered red in colour?
6.
Well, there are 3 of these and 3 more, so altogether that's 6, which I believe, oh darn it, 2 out of, try to do this, 3 out of 28. There, I believe that's, I can't count. 3 out of 26 there. Oh. Let's suppose you get some really ugly fractions or you're really tired like I was and I couldn't figure out what 652 simplified down to. 6 divided by 52. You see the ugly decimal? Hit the math button, choice 1. There you go, 326. Yeah, I'm randomly just going to pick 2 weird numbers.
Wait,
40.
how did you do that? Will you do that
Well,
again?
yeah.
Sorry.
Yeah. Let's pretend I'm doing 42 68ths, right? 42 divided by 68, hit enter. You'll get this weird decimal. Hit the math button, choice number 1. What that's going to do is take the answer and make it a fraction. And the answer is 21/34. So you can use your TI-84 to simplify fractions for you. Right, top number divided by bottom gets you the decimal. Hit the math button. Choice number 1. And there you go.
Thank you.
You're welcome. So let's make the sample space a little bit harder to do. I'm going to start off with a nice baby one and then I'm going to extend it. Imagine, one's over here. Imagine I have a class with A, B, C, D, E, and F in it. There are 6 students in this very small class. And I am going to pick one of you at random, and you're getting $10 because I'm such a nice person. The samples, when it's only one person being chosen, the sample space is kind of basically that list: A, B, C, D, E, and F. So the probability that A gets picked for the $10 is there's only one of that person out of 6. And there's your answer, 1/6. Now I'm changing the story. I've got more money, and I'm going to give it to 2 people. Right, so 2 of you are going to get picked from the class, and you're both going to get some money. Right, so let's go hunting for the sample space. Now, don't we have to figure out how many different ways you can choose 2 people? Now, if you just jump headlong and say A, C, C, E, and you're not, you'll get a lot of them. But you know the last couple are going to be murder to find. So it's much better if you tackle this in a more systematic way. So this is how I'm going to do. A, B means I chose A and B. Then I chose A and C. Then I chose A and D. Then I chose A and E. And finally, I chose A and F. And then I chose BC, BD, BE, and BF. I'll pause for a minute. Can you see there's a kind of there's a method to my madness here, right? It's not just random. Can you see I'm picking it in a very specific way? And if I continue this, won't I eventually get everyone? Before I do the next column, I've got A, B. That means I picked A and B, right? That's the 2 people I picked, right? Agnes and Billy, right? I picked them. And AC means Agnes and Charles, right? Or whatever. Why don't I have BA in my list?
You already have an AB.
Right. Does it matter who you pick?
No.
A, B, or BA, right? So AB means both of them, right? It's the same situation. How am I going to start the 3rd column then?
CD.
Then CE, then CF, agreed? And then DE and DF, and lastly EF. Do you see there's a nice organized way that we wrote those down? Agreed? Oh, another one I just thought of. Why didn't I write AA down?
Because it's the
There's
same
only one
person.
A.
Yeah, they're only one person, and you can't pick John twice or Agnes twice, right? Doesn't make sense in that context. Now, if you add these up, you get 5, 9, 10, 11, 12, 13, 14, 15. So what's the probability that I pick A? Well, now there are 15 things that could happen. And you might say A and somebody else. Yeah, but I don't care who the somebody else is because I'm A and I just want to know what's the chances I get picked, right? So how many ways could you be chosen here? 5. All of these. Agreed? Now, if you didn't have this written down, would you agree it'd be much more difficult to figure out the top and the bottom number? So I know it's a lot of work, but you kind of need to do the work to be able to answer the question, right? And by the way, have you noticed that your chances have got much better now? But doesn't that make sense that if they're picking 2 people, you get twice as likely to do it? Now, I could also use this to do things like this. What's the probability A and my pal B got the money? So I got the money and my pal B, she got the money. What's the top number for this story?
1.
Would you agree that's a lot less likely than this? But doesn't that kind of make sense? It's easier to get one person than it is to get both. Any questions about that process of creating a sample space and then using it to get certain probabilities? Okay, So let's move on to another concept. And that concept is called mutually exclusive events, or just ME for short. And not mutually exclusive events, which I'm just going to call not ME. Right. Little bubbles around them, right? Because nobody wants to have to write big words like that all the time, right? So you see me writing ME, it's just mutually exclusive. Well, what are mutually exclusive? So here's the definition. Two events, call them A and B, are mutually exclusive if they do not share any common events. So two events are mutually exclusive if they don't share the same event. Give an example. Simple one first. A is rolling a dice and getting an even number. Right? And B would be rolling a dice and getting an odd number. They are actually also, aren't they, two complements of each other? But complements not always the same as mutually exclusive. Sometimes they are, but it's not the same. So let me give you an example where they're not mutually exclusive. Sorry, they are mutually exclusive, but they're not complementary. Suppose A was you get a card and it's a heart, and B is you get a card and it's a club. Would you agree they are mutually exclusive? Right. There's nothing in the A that's the same guy that's in the B. Would you agree that they are separate from each other? Would you also agree that they're not mutually exclusive? Wouldn't mutually exclusive be hearts and not hearts, which would be, yeah, it includes clubs, but doesn't it also include diamonds and spades? So it's not exactly the same thing. Are we cool with that, that mutually exclusive isn't the same as
Wait.
complementary events?
So the first one is
It's both
mutually
things.
exclusive?
Yeah, this here, these two events are mutually exclusive.
Okay.
And they're also complementary. This one, these are mutually exclusive, but it's not complementary. For two events to be complementary, doesn't the second event have to be not the first one? Well, what's not hearts? Clubs, diamonds, and spades. You see, that doesn't qualify. Now, if two events are mutually exclusive, we can use this property. The probability that A or B happens is the same thing as the probability of A plus the probability of B. So if somebody said to you, what's the probability that you take some cards and you get a king or a queen? Then you could basically just stick them under 52. There are 4 kings and 4 queens, and there's your answer. Are we good? So if,
Sorry,
yes,
I'm still a little confused on how to classify something as mutually exclusive.
mutually exclusive means that the two events share nothing in common. If you're in the first event A, you can't be in the second event B. So any situation where the two events have nothing in common. You know, events are made up of 3 or 4 things happening, right?
Yeah.
Like hearts have 13 things in them, right? Well, the 13 things that are, well, let's do this one. The 4 kings and the 4 queens, would you agree that they are mutually exclusive? Kings can't be queens and queens can't be kings, right? They're totally separate from each other. That's what mutually exclusive looks like.
Okay.
Now, complementary sounds maybe similar, but it's not the same. If I said event A was king, what would the complement of event A be?
Queen.
No,
Or
it
Queen,
wouldn't.
Jack, or
And everything else that ain't a king. Do you see it's
Yeah.
a much bigger group?
Okay.
Right. So A and its complement together make everything. A and something that's mutually exclusive don't necessarily make everything. Don't they just have to be where we don't share anything, right? And because of that, they can be a bit smaller.
something that wouldn't be mutually exclusive is if A was a heart and B was also a heart.
Yeah, or let's do one that's not mutually exclusive then, right?
Okay.
Not mutually exclusive is when A and B do share something in common. So let's have A as hearts, and let's have B as face cards. These two events are not mutually exclusive. Aren't there some hearts that are face cards? I've got my little guy. Yeah, aren't there some hearts that are face cards? You see them down here? Jack, Queen, Jack, Queen, King of Hearts. They're face cards. These are not mutually exclusive then. Aren't some face cards hearts? I guess I could phrase it that way, right? So suppose I wanted to find the probability of A or B. So that I pick a card from a deck and it's a heart or it's a face card. This is going to be wrong. So don't write it down yet. Oh, I know how that works. There are 13 hearts. There they all are. And face cards. Aren't there 3, 6, 9, 12 face cards? I call this double dipping. Aren't we counting the same cards twice?
Yes.
Right. How many of those cards are we counting twice? 3. Isn't it the 3 heart face cards, right? The face cards that are hearts. So you want this question to be correct. Shouldn't you take away that 3 so you don't count them twice? Does that make sense? When the two events are mutually exclusive, can't you just do that and you're fine? Because they don't share anything in common. But when they're not mutually exclusive, don't you have to take account of the double dipping? Right. The fact that you're going to count some events in this group and at the same time in this group. So won't taking away 3 compensate for the double dipping, essentially? And so the correct answer in this case would be 22 out of 52, which is 11 out of 26. Okay, let's try another one of those ones. What's the probability that you get a red card or an ace? So 52 on the bottom. There are 26 red cards and there are 4 aces. Would you agree that these two things are not mutually exclusive?
Yes.
So how many are double dipped? How many have been counted twice?
2.
And that's the right calculation for this probability. So if you're trying to think, why do we need to worry about mutually exclusive? Isn't that a good idea to know if two events are not mutually exclusive? Because won't we have to adjust our probability calculation to account for it? In this case, I believe you get 7/13. On the other hand, suppose I went and said to you, what's the probability that you get a red card or a spade? Well, aren't red cards and spades mutually exclusive? Right. If you're a red card, you can't be a spade, right? And if you're a spade, you will never be a red card. So we can take the 26 red cards and add the 13 spades and everything is fine because there is no opportunity to do any double dipping, right? They don't share anything, so I'm not going to count anything twice. So a not mutually exclusive probability and a mutually exclusive probability. Don't they, although they're very similar, aren't they different enough to be important? Does that help?
Yes, thank you.
Right. So let's look at, well, we've already done the OR. So let's look at the probability of A and B and what we mean when we say that. When you say probability A or B, that's the kind of questions we've just done before. I haven't mentioned it, so I'm glad I brought it back. This OR is a very special version of OR. It's called the inclusive OR. The English language is kind of sneaky. Most people, when they use the word OR, use what's called the exclusive OR. In probability, this is the inclusive OR. So how does that work? If you were doing the normal version of OR, you might say to your kid, you can have ice cream or you can have cake. But when you say that, isn't it implied you're not allowed to get both? Your kid will say, I want both, but you ain't getting it. That is an example of the exclusive OR. But there is another version, the inclusive OR. What that says is you can have ice cream or cake or both. And these questions that we just finished doing, although you might not have noticed it, they were actually examples of that exclusive OR. Now, the word and is used in probability, and the way I think of and, the easy way for me to look at is, I think of it as what's the probability that you get both A and B. I kind of stick an extra word in my head. I don't write it down as I have here. So, for instance, what's the probability that you get a king and it's red? And the way I read that, right, is how many red kings are there, right? So how many red kings are there?
6.
There's, well, red kings,
2.
2, agreed? There's a red diamond and a red heart, 2. And so that ends up being 126. Let's do a different. What's the probability that you're a face card and you're black? So that would basically be how many black face cards are there? That's kind of how I would read it in my head. How many black face cards are there?
6.
Right, and that one, oh, I did this one earlier and I still can't make it work in my head. So we're going to be doing 2, so it's going to be 3 out of 26, isn't it there? Are you comfortable with the and? Probability of and. And doesn't care if the events are mutually exclusive. In fact, in a lot of ways, and needs them to not be mutually exclusive, right? There's got to be something that's in both. Give you a silly question. What's the probability then that you get a card, yeah, I'll get a card then. Do you get a red card and a spade? Now, that word and. How many red cards are spades? How many are both things?
None.
None. Do you notice that those two events then get you, those two things give you an event 0? Right. couldn't that be used as a test for mutually exclusive? Because if two events, A and B, are mutually exclusive, then won't the probability of A and B be 0? Because they don't share anything, right? Are we good? Any questions? Last chance. Can you show you some stuff in a second? That's a good sign. I like that. Last concept, and then we can do the homework. Some examples of homework. We're going to look at independent events. So you've got two events, A and B. So here's the definition. A and B are independent events. If the outcome of one has no effect on the probability or the outcome of the other. So if two events are independent, the probability that you get A and B will be the same as the probability of A times the probability of B. Very often the two events A and B are from totally different situations as well. So suppose A was you threw a coin in the air and you got a head. And B was you threw a dice and you got a 3. Then what's the probability that you get a head and a 3, right? You got a head and you did that. It's these two events are independent. Would you agree that whatever you get when you throw the coin in the air, won't it have no effect on the number that the dice is going to be? Would you agree that the two things don't interact in any physical way? And so that would be an example of that type of situation. So I could find the probability of the head and multiply it by the probability if I got 3. And a head is going to happen a half the time, and a 3 is going to happen 1 out of 6 times. So the chances that both those events happen would only happen 1 out of 12 times. Does that seem reasonable? Okay, time to look at some homework questions.
I was gonna say, could you do another one of those?
Oh, these ones? Okay.
Yeah.
Try and think of some. Let's have event A that it rains in Scotland today. And
We
let's
can't
say,
see your paper.
oh, sorry. Right, so the two events I'm going to pick are basically unconnected events, which is kind of most common ones, but you'll see later there are other situations. And let's suppose I tell you, because the weatherman told me, that the probability that it rains in Scotland today is a quarter, right? Got a 1 in 4 chance it's going to rain. And let's take B to be the probability that it snows in Peru. And the probability that it snows in Peru, I have no idea today, is 1 out of 10. So first we have to establish independence, and that really tends to be common sense. Would we agree that raining in Scotland is probably going to have no effect on whether it snows in Peru? Would you agree that they're far enough away from each other that the weather's not going to affect either? So those two would be considered independent events. The probability of one happening does not affect the other. In the next question, in the next situation, I'm going to have a situation where they would affect each other, and that would be important. But since these are independent, and you are being asked to find the probability of A and B, you just find the probability of each and multiply them together. And so in this case, it's 1/4 and 1/10. So you've got a very small probability that both of those things are going to happen today. And that's because A and B have no effect on each other, right? So let's see if I can put together two events that are dependent. A and B, you're female. Let's suppose that you go to a university and the probability that you choose somebody at random and they're an engineer is 1 in 100, right? So like 1% of that university are engineers. And the probability that you are a female, let's say it's a half, right? So it's a university where it's 50-50. Are engineers and being a female interacting in any way? Well, let me suggest that they do. Whether it's right or wrong, probably wrong. Aren't there many more engineers who are male than females? So the probability that I pick a female engineer, which is basically what A and B is, isn't it? Isn't that going to be a lot less than 1 out of 200? And so I wouldn't be able to just use the multiplication rule that you're allowed to do if you can say with a reasonable amount of confidence that the two things don't affect each other, right? Couldn't the chance that I pick a female engineer be a lot less than 1 out of 200, right? Maybe 1 out of 400 or 1 out of 500. I wouldn't be able to specify that number because I don't know enough information, right? I'd have to know everybody at that university, and I'm not given that. Does that help separate the independent? You're allowed to do it. Not independent, you can't multiply them. There's you need more information. Okay, I got nods on that, so I'm feeling good. Let's finally get to these homework questions. And, oh, I got a watch. I now know my own time. So yeah, Abra, thank you for doing the job last time. If I didn't already, thank you.
And a watch.
I bought a watch, $20. Hey, I splurged on myself.
Is it digital or is it like with the hands?
Oh God, you lot, just to get the curiosity over with. Can you see what it looks like?
Oh, that's pretty.
Oh, thank you. I get good taste.
Shiny and it matches your ring.
Oh yeah. Okay, so we're going to distract me. I might as
The
well.
term is analog.
Well, okay. I don't know if you can see this is my wedding ring. If you look really carefully, I don't know if it helps or hinders to do this. Do you see it's called a clodagh? It's a heart with two hands. Obviously, I'm Celtic, so that's not a surprise.
You can kind of see that it's engraved, but you can't see the engraving, but that's really sweet.
It is, isn't it? And this here used to belong to my dad. It's my ring. And you see the R. It's all in a
That's
row.
cool too.
Yeah, and if you look really carefully on the side, that's the Scottish national flower is actually a thistle, which is a weed with lots of spikes on it because it goes with Scottish personality. Right. No more distraction, Donna. Focus, focus. Right. Here we go. I hope. Here we go. Right. I'm looking this way because my screen's a little bit on the small side and I don't know why it's doing that. Right. Now, a student wants to send a bouquet of roses to her mother for Mother's Day. She can afford to buy only 2 types of roses. I guess you get like 6 of one and 6 of the other, right? 2 flavors, right? And she decides to randomly pick from bluebills, yellow, Sahara, and Aphrodite. Good. BYSNA, right? We are going to list of the 6 simple events in her sample. So they're telling us that there are 6 ways in which you can pick 2 out of that 4, right? Which one of those dots, 1, 2, 3, 4, or 5, are the 6 that they're talking about? Now remember, she's picking 2. 2, 2, 2, 2. Which of those 6 does the job? Which dot? Oh, I think you did, Eric, but I wasn't watching. What were you doing? 4. Let's check it out. Would you agree? They're doing it kind of the way I did it. Didn't they go BY, BS, BA? And then you shift along. YS, YA. Then you shift along SA. Can you see the 6 of them, right? That's the sample space that we were talking about. Now, assume that all of these are equally likely. What is the probability that she picks a BA? Isn't that essentially BA? Would you agree that there's only 1 BA out of 6? So I can't do this quite the way you can, but this is my best version. Can you see that the answer would be, in this case, a 6th? Right, so the chances that she chose that rather than any of the others is 1/6. Now, remember that AC means the complement of it. Here are some puzzles, and be careful before you jump in here. Are A and AC also mutually exclusive? If you take A and you take the complement of A, are they guaranteed to be mutually exclusive? Yes. Agreed? And one of these yeses is the sentence that you will use. Now, are A and AC independent of each other, which is a kind of trick question? No. In fact, aren't they the complete opposite of independent? If I know what's A, doesn't that directly affect what's going to be in the complement? That's like the total opposite of independent, right? Bit silly, that question, the second one. I like the first one. A penny and a nickel are each tossed once. Explain whether the outcomes for these 2 counts are as follows. Right. If you throw a nickel in the air and then you throw a penny in the air, right, and I guess one's a head, one's a tail, and that kind of thing happening, do they 2 events interact with each other? In other words, they are independent if they don't. Do you think throwing a coin in the air and getting a head, and then throwing a penny, I should say, and getting a head, and then throwing a nickel and getting a head, do they 2 things interact in any way? So if they don't, doesn't that mean that they are independent? And so it's one of these 2 yeses. They are independent. Yes, they are independent. The outcome from one coin does not affect the probability of the other. I like the answer. Yes, they are independent. The outcome of one coin, oh, the opposite sentence, right? Yeah, it's just a matter of an extra word. No. So yeah, they are independent. Are those 2 events complementary? It's throwing a coin, throwing a penny and throwing a nickel. Are those 2 events complementary? No, they're not even connected, are they? I mean, they're 2 different coins. I guess they have a head and a tail. So no, they're not. Are they mutually exclusive? Do they share anything in common?
They're both coins.
True. Do the events that happen, getting a head or a tail in both cases, do they share anything in common? Is a penny getting ahead the same thing as a nickel getting ahead? Or are they considered two different situations?
The same.
They're both heads, but are they exactly the same?
No, they're different.
They are different, right? So the bottom line is, although that they sound like they're connected, they're not, they're mutually exclusive. Oh, here's some probabilities. Keep track of your time. Suppose A, B, C, and D are all disjoint possible outcomes. Oh, then they had to use a word I haven't talked about, and that was my fault. So I'll tell you right now. 4 events or 2 events or 10 events are disjoint, right? Are just another way of saying that none of them share anything with the others. It's like a big version of mutually exclusive, right? Normally mutually exclusive you do with 2, but see if 3 events are, I would say mutually exclusive to be honest, but they're using disjoint. If 3 events are mutually exclusive, none of them share anything with the other 2. Does that kind of make sense? So it's like a big version of it, right? So if the probability of this is a quarter, and this is a quarter, and this is a quarter, and this is a quarter, so what would you say here? Yes, the sum of these probabilities equals 1. Right, if they share nothing in common, don't those 4 guys add up to 1? Now, if you get this guy, this guy, this guy, and this guy, listen one. If you're mutually exclusive, can't you just add up the probabilities of all of them? And in this case here, yes, and that's that. Suppose you and your friend Vlad enter a drawing for a free lunch by placing your business card in a bowl at a restaurant in week 1, and then again later in week 2. 1 winner is drawn each week. Events defined are A, you win in week 1, and B, Vlad wins in week 1, and C, Vlad wins in week 2. Oh God, I'm gonna have to keep this one going. Are events A, B, and C independent? Okay. There's nothing in this story that I'm reading that you couldn't win in 2 consecutive weeks. Do you agree? There's nothing says if you win 1 week, somebody else has to win the next week. So if you win in 1 week, will that have any effect on your chances of winning the second week? No. A lot of people think that because they've won once, that's their shot over with, right? There's no point gambling anymore. I'm not going to win, a week the next week. So they do count as that. Oh, this part B is interesting. Suppose that in week 1, the cards that were not drawn were kept and put into the bowl for week 2. He won week 1, didn't he? What happens to his card? Ain't there anymore. So he can't win in week 2, can he? So see with that extra piece of information, in the first situation, couldn't he win in both weeks, right? To pick his name out, to pick his name out. I think the way I'm reading that is that he can't, they are no longer independent. Okay, Jill and Zoe have lunch together. They flip a coin to decide who pays for lunch, and then they flip a coin to decide who pays the tip. That's not the way I would do that. When you flip a coin, you pay, I'll do the tip. If I pay, you pay the tip. Isn't that a fairer way of doing it? Couldn't you end up paying for everything? At least the way I'm reading that, you could end up paying for everything, which I don't think's fair, but never mind. We'll go with the story. List the simple events in this sample and define a possible outcome who pays for lunch and pays. Okay, so I'm going to have to come back to writing stuff down. So if you can bear with me. Let's try and write down the things that could happen, and I'll try and find a way of doing it. So J, they're telling me this. Use J for Jill and L for Zoe. And when I write down a pair like this, that one is going to be who pays for the meal. And that one there is going to be who pays for the tip. Okay, are we comfortable with what the two letters are going to be when I put them together? So, sample space. Couldn't you get Jill and Jill? Wouldn't that mean she pays for everything? Great. Now, do you see in this situation, is J and J, isn't that a possible thing? Remember my story at the beginning where I'm picking two from the class to get $10? Wouldn't J and J not work in that situation, right? So, you know, it depends on the story whether a double letter like this is valid, right? Can happen. Now, I'm going to try and figure out a way of doing this systematically. So how about J and Zoe? How about Zoe and J? And how about Zoe and Zoe? Would you agree that that's basically everything that could happen in this very simple story of paying for the meal and paying for the tip? Okay. Now it says, oh, these four guys, these four situations, might not be a sensible name, but they're called simple events. A simple event is just one thing that could happen, right? So in this particular story, isn't there four simple events that make up all the things that could happen? Are these simple events equally likely? Is it just as likely that Jill pays for everything, or just as Zoe pays for everything, or one of each, or one of each? If you're just doing a coin, right, heads you get it, tails you don't. Would you agree they're equally likely? Yeah. Any opinions? I'm saying equally likely, but if you want to disagree, I'm open to suggestions. We all happy that each one of these is just as likely to happen as the other? Do you know some people think this one here should happen more often than this one, but it's actually not true. Right, you throw the coin and Jill wins, right? Isn't the next one totally unconnected to it? Couldn't she also win again? In this case, winning means you pay for things. Interesting. So what's the probability that will Zoe have to play for both, right? Uh-oh. Would you agree it's 184? Because four simple events, one of which is that one. Here's a different question. What's the probability? One each. What's the probability that one of them pays for the meal and the other pays for the tip? One of each. How many numbers?
Half.
Yeah. Do you see how that splits? Right. Jill and Jill, 1-4, right? There's a 1 in 4 chance that Jill pays for everything. There's a 1 in 4 chance that Zoe pays for everything. And isn't there a 50-50 chance that they pay for one of each? Okay, that worked good. Let's nip back to our next question from the homework. Right. 2 fair dice are rolled, right? So you get one dice, throw it, other dice, throw it. The event A getting the same number in both has a probability of 1/6. Ooh. Interesting. Okay. Did you know that if you throw 2 dice, the probability that you get the same number in both, right? Both are 2s, both are 3s, both are 5s, right? Is a 6. It is true. We'll assume. I know it's true. They told us. Describe in words what the complement of A would be, right? What AC would be. There are 5 sentences there. What is the opposite of both dice being the same number?
Both dice being different.
Which would be the first thought. Agreed? Now, what's the probability of getting the complement? Now, you don't need to do an awful lot of work. Everything you need to know is in front of you.
Wouldn't that be 5/6?
And aren't we using the fact that a probability in its complement always add up to 1? So if you know 1, you get the other one for free. A fair coin is tossed. The chances that all of them are heads is 1/16, which is true. Describe in words what the complement of that is. What's the opposite of all of them being heads? And it's not none of them being heads.
All of them being tails?
Nope, it's not that either, but I can see why. It's a little bit sneakier than that.
At least one head occurs in the 4 flip.
Yes. Right, let me show you that one visually, because if I can ever get out of this one. We are looking at 4 coins being thrown, and the event, all of them are heads, ends up being 1/16. So I'm going to prove that. Then we're going to talk about what the complement would look like. So it'll take me a little bit of time, but here goes. All 4 coins could be heads, right? Then I'm going to do 3 heads and a tail, and I'm going to write them down in a very systematic way. Would you agree that's all the different ways 3 heads and a tail can happen, right? Now, if I then move on to 2 heads and 2 tails, it's a little bit messier to do, but I think I got them all here. If I do the 3 one, I think there's some more here, but let's move on. Let's do the 3 tails. That's it. Here's all my tails. So there should be 16. So what am I missing? 6, 6, 12, 13, 14, 15. 2, 4, 8. Who am I missing? 5, 10. I'm missing 1 from here. Okay, what combination of 2 tails and a head have I missed? There's 1 more left. There should be, based on symmetry, there should be a head here. Tail, head, head, tail, head. Should be a tail here. Head, tail, head, head, tail. Should be a tail here and head. There's the one I missed. That's it. Right, there are the 16 ways that you can get 4 coins. The probability that all of them are heads is 1 out of 16, right? There's 16 and only 1 of them is all heads. That's the A guy. Won't the complement of A be 15 out of 16, which is what the last answer is about? If you look at what is that compared to that, how you would phrase the complement, right? That's A, and this is its complement. The opposite of getting all heads is at least one is a tail. Does that make sense? The complement. If you wanted to phrase what's going on here, couldn't you say it as at least one of them's a tail? Now, couldn't two of them be tails, three of them be tails, four of them? But isn't there at least one of them got a tail in there? And we're finished with that question. We'll get time. I think I'm just going to keep it on this and I can read the question. It'll save jumping around too much. So this is question 9. Oh, won't do 9 yet. Suppose you are going to go and visit your friend for 3 days, and the probability that it rains every single one of those days, right, 3 days in a row, is 1 out of 10. Right, so that's your A. Won't the complement of A be 9/10? That bit we're pretty comfortable with. Now, how would you phrase the opposite of all 3 days raining? And think of using this as the beginning. What's the opposite, the complement of 3 days rain?
At least one of the days is sunny or not raining.
Or not raining, or dry, or whatever phrase you want, yes. Have you noticed that the complement of these tends to be at least one, insert the rest of the sentence here. In the previous one, wasn't this here the complement one? At least one is a tail. I could have phrased it, at least one is not a head. Wouldn't that be the equivalent? It mean the same thing. Okay, now move on to question 9. A brand of cereal contains a prize in each box. There are 9 possible prizes, and each of the prizes is equally likely to be in any box. Okay. Enter your answers as fractions, that's good. If you purchase 2 boxes, what's the probability that you're going to receive the same prize in both boxes? Now, you gotta figure out who the bottom number is. Now, when there's 9 things, as there is in this story, it's probably not a good idea to write down the sample space, you know, as a big long table. It's doable, but would you agree it would probably take you a long time? So we're going to use a different argument here. And what I'm going to do is tell you that you can actually calculate the number of things in a sample space without actually writing them down. And it's called the multiplication rule. Aren't there 9 prizes that could be in the first box? Aren't there also still 9 prizes in the second box, right? Because you could get the same whistle in both cases. If you multiply them together, do you see how 81 tells you the number of things in your sample space? Do you agree you do not want to write those 81 things down? So you got to have a workaround. And the workaround is, if it's 2 things and each one is equally likely, just multiply how many with the first times how many with the second, and you're good to go. Now, the top one's going to be a bit harder. You might say 1, but you'd be wrong. How many different ways can you get the same thing in this story? And it's more than 1. Remember, there's 9 things in each box.
9 times?
9. Does that make sense? And if the first thing's a whistle, right? One way you're getting 2 whistles. One way you're getting 2 dolls. One way you're getting 2 little guns, right? One way you're getting 2 hamsters, whatever it is, right? 9 things, right? One way of each, 9 things. And that simplifies down to 1/9. What about the next one, which is you receive 2 different ones? Now we know the bottom number is 81. Actually, I could jump right to the answer, couldn't I? Isn't getting 2 different prizes the complement of getting the same prize? And so if that's 1/9, can't I just call that 8/9? For the last thing I'm going to do for today, and we can come back and we'll do some more homework questions on Wednesday, is to show you why people have a false impression of probability. And what that tends to do is make them make bad gambling decisions. Well, all gambling is bad, but some gambling decisions are worse than others. I think it's one to spell it that way. The Monte Carlo, I think it's a Y there. Monte Carlo fallacy. What happens? Well, people think that probability tells you what's going to happen next. They have this feeling that the number somehow is influencing what's going to happen. So here's a very simple situation. Imagine that I've got a coin and there's nothing wrong with the coin. And I just played this game where you throw the coin in the air, and if you predict what's going to happen, 1, 2, 3, 4, 5, 6, 7, 8, 9. And 9 times in a row, it was a head. And you've just came into the casino and you're going to gamble, right? And the guy's going to throw the coin and you're going to put some money down. And if you predict it, you win some money. And if you don't predict it, he takes some money off you, right? A very simple gambling game. What is the probability that the next one is going to be a head? Nine heads in a row have happened. What's the probability that the next time you throw that coin in the air and nothing weird's going on, that it's a head?
1/2.
It's still a half. What happens in the Monte Carlo fallacy? There's 2 versions. Both are equally wrong. The first version is, hey, heads are in. Gamble heads, you're going to win. Look, the people who gambled there won lots of money. I'm betting heads. They think it's got more chance to happen. Why? Because lots of heads happened before. The other version of it is, hey, isn't it about time tails came up to balance it? It's meant to be 50-50 here. There's an awful lot of hearts. Shouldn't there be some tails by now? And they go and bet on tails, thinking that tails now has a better than 50-50 chance of happening. But statistically, or in probability, isn't the chance that the next one's ahead is still a half? You see how you can be caught out by thinking that the probability of a half is somehow influenced the next one. That's not how probability works. Isn't each event on its own? I mean, if you took it to silliness, if that was true, wouldn't the coin have to know how many times it was thrown in the air and that it was heads for the first 9? And it would have to say to itself, hey, wait a minute, I've got to get this averaged out. I'm going to try and bounce over to a tail the next time, you know, just to level it off. Can you imagine? That doesn't make sense, does it? You know, coins don't have memory. Monte Carlo fallacy. A lot of people believe that because something's happened a lot, that it means that it's going to continue to happen, or that it's time for it to flip and the other thing happens.